Welcome back to another episode of Heavy Wireless, a podcast that's part of the Packet Pushers podcast network. And today we're going to be talking about kind of a deep dive into a protocol called mDNS. And I have with me Bryan Ward, who gave a presentation at WLPC on this subject. But I wanted him back on the podcast to do a little more deep dive into the nitty-gritty of the things he found on his network with respect to mDNS. Bryan, I'll just let you get started. What was your problem with mDNS? How did you figure it out, and how did you solve it?
All right. Hey, Keith. Thanks for having me on to talk a little bit more about this. As you mentioned, this is kind of a follow-up to a talk I did at WLPC. I'm sure Keith is going to put the link to that recording in the show notes. I did a heavy networking episode with Ethan shortly thereafter, but Keith wants more. Happy to provide it. Yeah, let's go into a little more detail, and hopefully I'll get into the tech aspect of it at more of a Wi-Fi expert level that some of the listeners here would probably appreciate. Just quickly about myself, you had asked me to do that. I've been doing IT professionally for over 2 decades now. I had that sad realization recently the other week that it's been that long.
When you start counting things in decades, it makes you feel old.
It sure does. And thinking back, it's like I first got into radio. I got to thank my grandfather. He gave me a Uniden Bearcat scanner. And I just, tuning up and down the band, listening to everything I could find. And it's like, ooh, what's that strange signal? Been doing Wi-Fi since the early 2000s when I bought my first PCM-CIA 11B adapter. I've got my WRT-54G kicking around somewhere still. It still works. I've done some very interesting Wi-Fi and other wireless technologies for the entertainment business. My first point-to-point link was actually for Cirque du Soleil. But most recently, I have been working in higher ed. I'm currently the lead network engineer on a college campus, and I deal with everything layer 1 through layer 8. My specialty is in Wi-Fi, however. We're currently in the middle of a major campus-wide upgrade. 200 buildings, everything from small dorms with 12 students living in it to lecture halls with 500 people, athletic venues, a little bit of everything. And when I first arrived at Dartmouth, I kind of inherited the existing controller-based Wi-Fi network. Very quickly found out that RF design was not part of the process. It was red solo cup, if that. Dartmouth put in its first AP locations in, the middle of a hallway back during 802.11 prime testing when Wi-Fi was just a curious experiment. It wasn't even a nice-to-have technology. The locations were never really considered. APs got spotted in as response to trouble tickets. And now, as we all know, Wi-Fi is the primary means of connectivity. We hypothetically asked students, if we had to turn off water or Wi-Fi for a week, what would you choose? And they all chose to turn off the water. So since RF design was non-existent and we were spotting in APs, we were still getting trouble tickets. Like, hey, I'm sitting in a room under the AP and I'm still having connection issues. So it's obvious it's no longer a coverage problem. You've got great signal strength from the AP. Why is the user having a bad time? So we started to look at other possible causes. Various TAC cases were opened, and eventually one of the TAC engineers said, oh, yeah, maybe you should turn off mDNS traffic and turn on client isolation. And that helped things well enough that we could stop worrying about it and move on to other projects. And ever since then, it's been, okay, well, why did this fix it? What is this mDNS protocol? Why is client isolation, those single checkbox there, a magic fix for all these problems people have been having? And over the past several years, as I've continued to study Wi-Fi and related technologies, I realized, oh, it's all just airtime. Everything about Wi-Fi is about airtime. It's the one thing we can't get more of, aside from, regulatory changes. 6 gigahertz, woohoo. And as we all know, airtime is shared by all devices, not just 802.11, but other devices using the same frequency. And if we're filling up this airtime with what I'm going to call garbage traffic, we have less airtime for what's considered important traffic. So mDNS, I'm going to definitely put into the category of this garbage traffic. And it's not the only protocol that does this. There's a lot of broadcasty, multicasty traffic that you probably just don't care about on your network 99% of the time. but it's using up a ton of airtime. So when we think of airtime and contention, you might think, well, what about QoS and WMM? And can't we say some traffic is more important than others?
Well, they're magic fixes, aren't they? You just turn on WMM and it magically fixes everything.
Oh, yeah. That's what that checkbox does. I mean, you turn it on and walk away and say problem solved. You don't have to think of it ever again. No, that's actually not the case. The magic fix is more bandwidth, as Greg would chime in here and say if he were with us. But again, we can't get more bandwidth. We don't have more RF airtime. We don't have any additional frequency spectrum. So QoS does help prioritize some traffic over others. This voice traffic that I'm sending to you over a Zoom call is being tagged as voice priority. And the access points and the routers on my network are saying, oh, that's more important. Let me egress that through my ASIC first before anything else. That only works if all the devices on the network are respecting that and are properly marking the traffic. I shockingly discovered, that some Apple devices are tagging their mDNS traffic as voice priority. So you've got this, iPhone or iPad announcing, hey, I'm an iPhone. Look at me, I'm an iPhone on your network. Which, okay, great. Some of their applications depend on that. But is that voice priority traffic? I certainly don't think so. Yeah, it makes the drop-down list in the settings window a little more snappy. You click find printers or find, AirPlay devices, and yeah, the list will populate pretty quickly. But does it need to be taking priority over voice calls?
It all depends on, if you're Apple engineers and you want your stuff to look good, they've found a secret, a little trick.
They found a trick at the detriment to everything else on the network.
You can see why that might make sense. I was trying to explain this discussion I was going to have with you today with my wife last night and explain to her how mDNS works and how she has an Apple, and if she wanted to print, this is how she finds it. And she's like, that works great. I like it. I said, now expand it out to 50,000 devices. And she just got this look of shock on her face like, well, do they do the same thing? Yeah, that's kind of the problem. They do the same thing.
That's my big sticking point with mDNS and other similar technology. It works great at home. It works great in a small business environment. But as you just said, scale this up to enterprise. I have a dorm with 500 students living in it. That's a lot of airtime being wasted for mDNS announcements that are generally not being used. The printer sitting next to me, I don't need it announcing every 5 seconds, hi, I'm a printer. Well, yeah, I already know. I've already connected to you. I've given you a static IP address. I don't even need your announcement. And yet it's still going to be announcing that.
So how did you find out? You fixed it by just turning off mDNS in client isolation. Mm-hmm. What made you think turn them back on, even for a test?
In my research of this problem and in my preparation for my presentation, I looked and it's like, hey, has anybody actually tested this? If you read the configuration best practices from vendors or read the textbooks, it's like, yeah, you should block this. You should turn this off. Okay, why? Everybody knows you should turn it off, but why? And I was unable to find any real data about what's going on, why this is a problem. I'm lucky enough in my environment to have some colleagues at the engineering school who just love this kind of research. They were the number one complainer of this congestion issue. Like, hey, I'm sitting under the AP you just installed. It's a top-of-the-line access point, and yet my throughput is still so poor. Why? They wanted to fix it, and they wanted to understand why. So they graciously allowed me to say, hey, can I use your entire building as a test bed and check this one box or uncheck this one box and record some data and see what happens? And they're like, we'll have to get formal approval, but yes, we want you to do that. So we scheduled a day with them. I wanted to record for a full 24 hours of allowing mDNS and allowing client-to-client traffic. Normally, we have it filtered and turned off. I wanted to undo that change and record and see what the difference is. And if you look at the graphs in my slideshow from WLPC, the difference is immediately visible. It goes from essentially a flat line of just idle network utilization to maxing out 100% RF usage. Like, you cannot fit another frame into the air if you wanted to, with this traffic being allowed throughout a building.
And how many devices did you collect this on in that building?
I was able to capture airtime usage and packets for 408 APs. There were about 1,500 clients total connected across 3 buildings, over 400,000 square feet. We operate 2 production SSIDs, .1x eduroam network and a guest network. And over the course of an hour-long test from 12:30 to 1:30, right in the afternoon, I captured over 500 million frames on the wire, as well as over an hour's worth of airtime RF spectrum usage. So full production network, capturing everything I could get my hands on. I captured every single packet, every full packet that hit the wire. I did not want to use NetFlow. If I was going to do this research and come up with a definitive conclusion, I didn't want to have to put the caveat at the bottom. It's like, well, this was a 10-to-1 sample and this might not be accurate. I captured everything. So I worked with our research computing team. They had just installed a new fancy high-speed network attached storage system. They gave me some space on that, spun up some VMs on a VMware host that was about to be retired. So I had 512 gigs of RAM, 24 CPU cores, 10 gig network connectivity into this capture appliance.
It's a little sad that you threw that much hardware at just doing a capture. But I guess if you're going to go for, that's overkill.
Yeah.
But did you even get close to taxing that hardware?
Some of it, yes, actually. Some of the threads were running at 100% at times. From what I recall, I was streaming out to this network attached storage at a constant 4 gigabytes per second. So it was a very constant stream of data.
You collected a lot of data.
I collected a lot of data. I actually used a product from NTOP called N2 Disk. This is like TCP dump, but it's engineered to be lightning fast. They've essentially rewritten TCP dump from the ground up for performance benefits, and it can capture 10 gig line rate on just commodity hardware. It's very impressive. If you work in higher ed, they will give you a free license for this. Take advantage of that.
So what did your data show?
My data showed it's not just mDNS. That is the problem. It's really any broadcasty, multicasty traffic. And other protocols include things like SSDP, Simple Service Discovery Protocol. That's what UPnP, unplug and play, your universal plug and play, uses on a home network. LLMNR, link layer, multicast name resolution, is kind of like Microsoft's attempt at mDNS. Dropbox is a very popular application on my network. It has its own broadcasty, multicasty discovery protocol called Dropbox LANSync. If you saw my presentation or if you're looking at the graphs, you probably remember the slide where I said, oh yeah, and let's throw in Windows networking traffic. And that just blew everything else out of the water. I mentioned at the time I was presenting at WLPC that I wasn't quite sure why that was the case. Well, in the months since I figured it out, it turns out we had a global misconfiguration on the network, which essentially turned every device into a broadcast node for Windows networking.
Oh, like a repeater kind of thing? Or
like a repeater. It wasn't trying to use the Windows networking infrastructure from the domain. It was just saying, nope, let's broadcast all these lookups. So that's why that massive jump in traffic appears for that protocol.
I'm assuming you found the checkbox to turn that one back off.
So the good news is with client isolation features turned on in the Wi-Fi infrastructure, that was also being blocked.
So part of the problem is when you just do that, I'm blocking all of this traffic, you don't know what was causing the trouble. You fixed it, but you didn't know why it got fixed.
It's this total sum of this broadcasty, multicasty, discovery garbage traffic. While we're talking about mDNS as the topic of the presentation and the topic of the talk, it's not fair to say that mDNS is the only culprit. It is, aside from this Windows networking misconfiguration, mDNS is the largest contributor to this garbage traffic, but it's not the only one.
So do you think after looking at your data, if you only turned on client isolation, did you ever try turning one of the two off?
So they really work hand in hand. You can have client isolation turned on, but then still permit mDNS. A lot of vendors have that as kind of a separate checkbox, block everything, but still allow mDNS. And I feel like that's been put in because a lot of applications depend on mDNS. And when you allow it, things just magically start working again like they do at home. I did not try it in that configuration with client isolation on, but allowing mDNS, because the data that I captured still shows that, it's still going to cause problems. There's so much mDNS traffic that it's going to eat up the airtime. Looking at the graph, I was averaging about 300 to 400 packets per second of mDNS announcements. That's a lot of data to be using up airtime.
Stunning amount.
A stunning amount, yeah. Beyond that, SSDP and LLMNR were about 50% of that. Dropbox is very chatty. So there's lots of protocols. I had a long list of other protocols I discovered when I was doing this packet capture. I presented really just on the top handful, the top talkers.
I think something you've done with all this data, and we're all grateful that you had the resources and the ability to pull that off, was a lot of developers, it sounds like, have found, I don't want to say cheats, it's a protocol, they're just using the protocol to enhance their individual application's performance without thinking of the ramifications on the network.
Yeah.
And if their test bed was small, they wouldn't even have noticed it.
Correct. Yeah, if you're developing an app or a device and you've got maybe a half dozen of them connected to a wireless LAN, you won't see this as a problem. It's at scale when it becomes problematic. This is why mDNS works really well at home and in small business. It's not a significant portion of the airtime. There's enough airtime left over that other more important traffic can still get out.
It's just when it starts to aggregate with that many devices at the same time. Did you find any other possible solution in segmenting? So some vendors call it geofencing, or there's ways they can block mDNS and keep it contained within certain regions.
Yeah, so I know a lot of people are probably thinking, well, what about a bonjour gateway, or grouping my clients together, or hey, my vendor sold me this secret sauce that they claim fixes it. Those technologies do exist, but you need to understand what they're doing. Bonjour gateways are not the check this box and magically things are better. A bonjour gateway is a proxy. It's a router almost for that application layer traffic. And they're used for when you're offering a service and you want to announce it via mDNS. So one example is with printers. Say I have a wired VLAN with a bunch of printers on it, shared, any student can use it printer. That's obviously on a different VLAN than my wireless clients. But what if I want to announce those printers via mDNS? Well, a bonjour gateway can do that. It can receive the mDNS announcements from one VLAN and rebroadcast it out to another. It's inter-VLAN routing, but at an application layer. So that way I can still have mDNS filtering turned on the wireless network. I'm not rebroadcasting mDNS traffic from my wireless clients, but I'm still broadcasting out this mDNS traffic being sourced from another wired network.
Does that bonjour gateway take mDNS and unicast it on the second VLAN?
It depends. We have to understand how wireless 802.11 multicast is functioning. If you're operating just a flat 802.11 network, all clients are on the same VLAN, maybe like a WPA2 personal with a PSK, it could actually use multicast, 802.11 multicast as the mechanism by which it transmits that. So one frame being sent at the minimum basic rate being sent to all clients within earshot. However, if you're using a .1x network where you're bridging into different VLANs depending on your authentication, well, you can't just use 802.11 multicast because I've got a faculty laptop and a student laptop on different VLANs. They should not be hearing multicast traffic from each other's VLANs. So a lot of vendors, their implementation of 802.1x authenticated Wi-Fi means that multicast turns into unicast, and it unicasts it to every client within a certain VLAN. So if you calculate the airtime, a minimum basic rate multicast frame does take longer than a unicast frame at a higher rate. But if you're unicasting to 100 clients, total airtime, it's going to be longer than just the single multicast frame.
So like you said, there's not just a simple checkbox to say, oh, turn on Bonjour Gateway, solve the problem.
Correct. Yeah, I was reading through some vendor documentation, and there's vendors out there who are aware of this issue or this consideration, and they say, okay, well, I will unicast this multicast traffic to my clients until I have more than some number of clients associated. So I think it's like if there's more than 5 clients associated to the AP, it's going to do 802.11 multicast at the minimum basic rate, because that actually uses less linear time. And the APs are calculating, okay, do I unicast it to multiple clients or multicast it to everybody? The APs are calculating that and making that decision on the fly. So yeah, some vendors have put a lot of thought into this problem, and there are some really clever solutions for it. If mDNS is something you're actually using on your network and it's something you're supporting, look and see how your vendor actually supports it under the hood. If you've turned on a Bonjour Gateway in an attempt to say, fix the problem, go and make sure that that isn't causing more trouble. You make sure you've got it set up right. Again, Bonjour gateways are if you are offering services via mDNS, or you need mDNS to traverse between one subnet to another.
To finish up this great deep dive into this, after you've done all this data, what was your end solution? Did you just go back to the simple checkbox, or did you make some changes before you turned everything back on?
I set it back to the way it was, because that has been and is continuing to work really well in our environment. So we are still blocking client-to-client traffic, and we are not allowing mDNS as an exception to that. I actually discovered that there's more filtering that I probably could be doing in addition to just this. We're no longer using a controller-based network. We're dumping our wireless client traffic off locally in our current architecture. There are some interesting layer 2 ACLs that I could implement on my network switches to try and filter out some more of this. It's best to block this garbage traffic at the source if possible. That's going to be pretty hard to do, but if you are working with a lot of Windows machines and you have a domain and you can push group policy, turn off the mDNS features, turn off LLMNR. Tell your clients to not do link layer name resolution in any protocol unless that's something you're actively using on your network. It might be interesting to go over how and why clients are doing link layer name resolution. There's this scenario that I think it explains it pretty well. So imagine you open a web browser and you type in the domain name of your favorite website, but you misspell it. What happens, Keith? I misspell packetpushers.net. Well, what does the browser do? Does the browser know that I've misspelled it?
No, not at all.
No. So what does the browser do?
It just forwards that frame up and tries to find it.
How does it try to find it? The standard C library provides a function called getAttr.info or getHostByName. And that really just says, hey, operating system, I need to resolve this name to an IP address. It's up to the operating system to determine how to resolve it. First, your OS is probably going to look in your local etc hosts file. It's like, oh yeah, that's part of every DNS lookup, isn't it? Yeah. So etc hosts, or the equivalent on your operating system, is where you can statically assign name to IP mappings, kind of like static ARP on a router. Usually the file's empty and your OS quickly skips past this step. So assuming the name you're looking for isn't in that file, it's probably going to send out a regular DNS query to the configured DNS servers, be them manually configured or via DHCP. And it's probably going to send out more than one DNS query. It's going to look for an A record and a quad A record. It's going to send it out dual stack if you are running both v4 and v6 on your network. It might try multiple DNS servers as well if you've got a primary and a backup, or you're doing some sort of round robin. Ideally, the DNS servers are going to respond with an NX domain, like, hey, this domain doesn't exist, assuming no attacker is squatting on it. Then your OS is going to say, all right, I couldn't find it via normal DNS. Let me try mDNS. It will send those same queries out on your local network.
I did not know that when it failed, it would switch local.
Yes. So every time you fat finger a domain name, your OS is going to do everything it can to try and resolve that. And if your operating system is running mDNS or other, Windows networking LLMNR software, a lot of them are, it's going to fall through and try mDNS. You can fire up Wireshark and give this a shot. Look for mDNS and DNS traffic in a Wireshark capture and type in some bogus domain names into your browser. You will probably see mDNS queries.
I will take that challenge. Thanks for sharing that. I didn't know that the failure would trigger. Is that just a Windows thing? Or do you know other OSs that do that as well?
It's all OSs. In Linux, you can actually see that this order of operations is defined and configurable. I mean, it's Linux. You can configure everything, right? So if you look in etc nsswitch.conf, that file will have a line in it that says hosts : file DNS mDNS. And that defines the order of the technology that the operating system will try to resolve the name.
So etc host, straight DNS, and then finally mDNS.
Correct.
Have you tried editing that file and just dropping off the last mDNS and that clears it?
Yeah, you can delete that and your operating system will no longer fall through and try mDNS.
But that's a really tough thing to push out to all of your clients.
It is.
Especially when they're not your clients.
Yeah. So, circling back, it's like if you've got a fleet of Windows machines managed in a domain, you might be able to push a policy and turn this off. You are not going to be able to turn it off on every student's iPhone. I don't even think that it is a setting on an iPhone.
Well, I'm sure it's a setting. Whether or not you have access to that setting is something different.
Yeah, someone somewhere at Apple has access to that setting, but it's nothing that's user-facing.
Knowing they have a tendency to think local rather than enterprise, I'm pretty sure they're going to be doing the same thing. Well, Bryan, thank you for sharing your expertise and even those hints. I think if you're interested in these things, we'll have in the show notes both his blog on this, his WOPC, as well as a previous podcast episode that Bryan did with Greg. Thanks for your time, and hopefully people will follow up on this and look internally, and when they find their own issues, be able to share them with the rest of the community. Thanks for your time. You've been listening to another episode of Heavy Wireless Podcast, part of the Packet Pushers Podcast Network, and we're glad that you joined us for this time. Look forward to hearing and talking with you in the future. Thank you.